Ready? In this video, we're going to talk about ionization energy, which is inversely related to what we learned about in the last video, which is the size of the atoms with respect to their trends on the periodic tables. Ionization energy is the energy required to remove an electron from the ground state of a gaseous atom or ion. Basically, how hard it is to pull an electron off. The higher the energy, the harder it is to pull off. And then we're also going to look at subsequent ionization energies. So the first ionization energy is the amount of energy required to remove the first electron. Second would be the amount required to remove the second electron, so on and so forth. And this is going to be completely related to how many electrons the atoms have in their outer shell. So what you can see is that let's take a look at magnesium, for example. Removing the first electron requires 738 kilojoules to remove a mole, one electron from a mole of these atoms. And you can see that that number goes up as you remove the second electron. The reason that happens is once the first electron is removed, the number of protons stays constant, but the amount of repulsion you have in the electron cloud goes down as an electron is removed. So it takes more energy to remove the second one because now that outermost electron is going to be closer to the nucleus. Now magnesium has 2 electrons in its valence shell, which means that after you remove those first 2 electrons, you're going to be removing an electron from an inner shell, which is significantly closer to the nucleus. And what you can see here is that the jump in energy, it goes up by about 700 here, and then it goes up by a substantial amount going from removing the second electron to the third, because the third electron being removed would be from an inner shell, and that would be much harder to take away. Now, with respect to first ionization energies, you can see an obvious trend here. You can see that the smaller elements, which are up on this part of the periodic table, require more energy to pull electrons off of. Again, using Coulomb's law, the distance between the oppositely charged things has a large impact on the amount of energy or the force of attraction there is, and therefore the amount of energy required to take it away. So you see it, but there are a couple breaks in this trend. You can see that to go from beryllium to boron, it actually takes less energy to remove an electron from boron. And this is why. If we draw the electron configuration for boron versus beryllium, so if we have beryllium, it has in the 1s, you have 2 electrons, 1, 2. To take this electron away from the s subshell takes more energy than it would to take away, when we look at boron, an electron from out here. The p subshell is actually considered higher in energy, and it's a little bit further away on average from the nucleus than the s subshell. Therefore, it's going to take less energy to remove that p subshell electron that you would with boron as compared to an s subshell, which is closer to the nucleus on average, lower in energy, to take that away. There's also a second break in that trend going from nitrogen to oxygen. And the reason for that has to do with the fact that if you're removing an electron from nitrogen, you're removing an unpaired electron, and it's following Hund's rule, and you have a nice stable p subshell that's balanced out. When you're removing an electron from oxygen, you're removing a paired electron. The added repulsion from having another electron in that orbital makes it easier to pull that electron away from oxygen than it would be to pull away the singled up electron that you would be removing with nitrogen. So that just explains a couple of the breaks in the trend with respect to ionization energy. So again, the energy required to remove an electron from a neutral element, and it goes up as a function as the atomic radius goes down. So they're inversely related.